Symposium. We have just one speaker today. That's going to be Haiying Zhu from NCAR. And Haiying's going to be speaking to us about the Asteroseismic modeling portal. So one of the unique things about the Gateway program and really Exceed in general is kind of the diversity of science areas that we get to work with. And AMP is kind of a unique gateway in that it does very computationally intensive simulations, and it's sort of a unique application. So what they're looking at is the ability to derive properties of sun-like stars by observing the natural vibrations. And so there is some work, especially with NASA's Kepler satellite mission, that the AMP gateway is very uniquely tailored to do. And so Haiying's going to talk to us some today about her work on that gateway and the sorts of things that she's been doing through the ECSS program. So I want to thank Haiying for preparing a nice talk today, and I want to thank all of those of you for joining the call. And with that, I'm going to mute myself and let Haiying take it away.
Thank you, Nancy.
Wow. The thing is still.
Hello, everyone.
Wow.
I heard a little bit of background noise, so I'm going to go ahead and mute the participants now. I'll open it up for questions at the end, or if people have questions they want to send via chat throughout Haiying's talk, that'll be fine too, and I can field those. So just a moment, and I'll turn off the background.
Presentation mode is now enabled.
Okay,
Hello.
Great. Please go ahead, Haiying.
Thank you, Nancy. Hello, everyone. This is Haiying Xu from NCAR. Today I will present Astroseismic modeling portal development. This gateway is developed by Matthew Watsky, and then I supported from 2011. And the PI is Travis Metcalf from Space Science Institute. Let me talk about the background about this gateway a little bit. This gateway is based on Asteroseismology. Asteroseismology is a powerful technique to determine the ages and the other properties of field stars. Those other properties include compositions like radius, masses, or heavy element mass fraction, or helium mass fraction. So using this gateway, we can generate the diagram for the stars. And now it showed a Echelle diagram for star KIC A379927. This is a typical example. It shows the match to the frequencies of the scaled solar surface correction of CD has been applied to the raw model frequencies. Different symbols are used to indicate the radius, dipole, and the quadrupole, and the octupole oscillation modes. Open symbols are observations, so it shows observations are very matched to the generations. This is another diagram called a spectroscopic Hertzsprung-Russell diagram for the star KIC A379927. This is a solar composition evolution tracks from Arher's evolution code for masses between 0.75 and 1.75 mass in solar units. Are shown in dotted lines, but the solid blue lines shows the stars, and the specific star's mass is 1.15, and the axis shows the temperature is around 6,000 degrees. So using the science code that developed by Travis Metcalf, we can get more precise stellar properties. This in this slide, 42 selected for seismology, which are blue, and 34 selected for exoplanets, which are red. There are some disagreement for most massive and youngest stars, but fitting frequencies improves precision of properties by 2 times or better. So you can see AMP increase the precision than the Chaplin for around 2, but for age is maybe around 4 times. And then AMP compared to Hubbard methods is still around 2 times better. Our gateway is based on this a parallel genetic algorithm and stellar evolution code and a diabatic pulsation code. The Asteroseismic modeling portal is a web-based interface to the stellar modeling pipelines. It uses this genetic algorithm on exceed supercomputing resources to optimize the match between Asteroseismic models produced by stellar evolution code and a diabatic pulsation code and a given set of observational constraints. In the following, I can show you the 2 modes that these codes are used. First one is a forward model. Just start with a forward stellar simulator, which is called direct ASTEC model. In this model, a scientist specify a star's parameter, and the model is generated by this ASTEC codes. Then we can get observators and including Echelle and HR diagram are produced. So you can see the diagram that I introduced before. Then the science has another code, which is optimization code. It is trying to find a model that fits the observation the best. This one allows astronomers to determine the property of sun-like stars by analysis of their oscillation periods. It uses a parallel genetic algorithm to optimize the match between the codes and the observations, then try to choose the best stars, adjust the population, then run the codes again, then find the best stars again. So in several iterations or hundreds of iterations to get the model. In AMP in this uses several constraints to improve this match precision. Those constraints including frequency that's most used, and also some spectrometric constraints or luminosity, and also the radius are used. So it improves the precision by 2 times than all the other methods. In the computational cost, this gateway has been running on several different resources. It first run on Frost, which is in NCAR. Then they are tested on Big Red and the Lone stars. Later they run on Kraken during 2014. In 2015, gateway is running on STEMP. So you can see the cost is reduced a lot, but on STEMP it should reduce more. So in the future, we will optimize the science code a little more efficiently to best use the STEMP resources. Here is the AMP portal workflow. User interact with a web server, grid processing on a daemon server, only communications through a SQL database, which is in the middle. Web interface attribute preparation, where a user login, record authentication instant and IP. When a simulation is submitted, associated with this authentication record, append only database tables and backup log files. Grid AMP daemon attribute processing. When processing a job, the recorded authentication instant is tied with it, caching the generated certificate. Lifetime limited by the community account certificate lifetime. Every simulation use the same community account certificate proxy. So in the future, we may use GSI-SSH instead of GRAM now, which we use GRAM now. So grid AMP accounting data retrieval, user returns grid job ID to get job status information. And then grid AMP submit all the job to Frost, or Kraken, or STEMP, which are all exceed resources. In 2013, all these servers, which is in the blue rectangle, are moved from NCAR to Aarhus University. We will detail that in the future, in the later slide. Here is the input parameter interface for the user to use. We can type in the mass and fractions and all the input parameters, or you can upload by a file. Here is the result page. Result page on the you can see on the left side is a very long page. So you can see the you can show the run status by this green rectangle, and show all the description of this jobs, and here we can see the input parameters that user input set up from the files or from the interface, like frequencies, arrows, boundaries, and sphere degrees. Here is the results that got after job finished, and we get the mass of the star and the heavy element mass fractions and the helium mass fractions and luminous and the frequencies, all the information that a user want to get. Here is the result plots that generated by the after processing. Then we can see Echelle diagram and Hertzsprung-Russell diagram. And you can download the results by click these blue links. So it's very convenient for people, for users. And also, most important thing that is shows here, you can see the algorithm that used and results shows on the here. And also, you can see the iteration that has been run for each job, and also how much SU is being used for each job. So if user want, if scientists want to improve their code efficiency, they can using this results page to know how fast it's improved, how efficient it's improved. This gateway has been running for 8 years, since 2007. NCAR, who is Matthew Watersky developed and maintained. Then I supported from 2011. And in the account from the website, I can find out that there are 110 astronomers has been registered to the gateway, and 18 or around 19 million SUs has been spent, and 30,000 jobs has been submitted. Also, you can see from this progress plots that from 2007 to 2009, we used the Global Toolkit 4, then we upgrade to Global Toolkit 5. In 2005, we upgrade to Global Toolkit 6. And it's been running on Frost for more than 3 years, then on Kraken for like 4 years. And in 2014, we moved from Kraken to Stampede. And that I did all this moving stuff. And for recent activity, in 2013, I moved all the virtual servers, including web interface, web servers, daemon servers, and database from NCAR to Aarhus, Denmark. Because all those servers has virtual image, so we just copy our virtual image and send it to Aarhus. This way, we can relocate all the servers very efficiently. In 2014, we changed the supercomputing resources from Kraken to Stampede by the help of Stampede staffs. So we can enable all the functions of the AMP, like job chaining and job logging. And in 2015, we upgrade OS and its related software of daemon server, because we have to move from the TerraGrid proxy from TerraGrid to proxy at Exceed. That's I have to upgrade my proxy and OpenSSL and also the Global Toolkit. So I upgrade all the software, but the operating system upgraded by Aarhus administrators. In the future, we will replace the GRAM job submission to GSI SSH submission, and thus we can use that Perl script to collect individual information as well. Then we'll optimize the scientific code. This will be done by tech staff. That way we can make the best use of the Stampede and supercomputing resources or any future supercomputing resources. Also, I will upgrade more servers such as database servers and web interface servers. So that's it. Any questions?
Hi, Ying. Thanks. Let me open up the lines here. There is at least one question for you, and
Presentation mode is now disabled.
Okay, Sergio, do you want to go ahead, please?
Yeah, sure. Very nice talk. Thank you. It's not clear to me what the relationship is between these simulations and actual data from, say, Kepler. Where do the data figure into maybe specifying the inputs or validating the outputs, or can you speak to that at all?
Yes. So, like, in this, if you see the slides in this optimization mode, so the optimization mode, so those data will be used to match the Aher's evolution code to best match, to find the best star. Yeah. So that's why.
So there's somewhere in the diagram, not explicitly shown, is a database of the observed results, and that somehow is fed into. I mean.
Yeah, I think so, and also I think Travis used those data to generate maybe some especially the frequency constraints with some error bounds, then can be fit in this model. Fit in this model. So he has been check all the data, Kepler and all the data. Yeah.
I mean, because it occurs to me that in right now, I guess in all of EXCEED and more generally, the big emphasis is on combining HPC methods and data analysis. Mm-hmm. So it would be really interesting to see more details about this process, because this seems to be a very interesting case where, we have modeling going on, but we're kind of doing, data, what some might even call, data assimilation, or at least, feeding data in and establishing this process between, optimizing simulation runs based on data, which may or may not be big, but so some details on how that's done, I think, would be probably very instructive to many of us.
For the Kepler data, I think because there are so many users has been used that data already, so they must got the properties from those data already. I think Travis just feed in those properties directly, just use those properties directly. He didn't use those data anymore, so we didn't have those data analysis in this model here.
Okay, so he used pre-processed data in order to do this, but that process in itself, or that aspect, I think personally, and maybe others, I'd like to hear more about it. So.
Yeah. So that maybe I have to ask Travis. Definitely have to ask Travis. Yeah, how they do it. Sure. Yeah.
Thank you very much.
No problem.
Yeah, thanks. I had sort of a related question to Sergio's. It seems like there's maybe a populated database that has the star properties and vibration properties, and then what the scientist is entering into the gateway is observational vibrations that they see from their current use of a telescope, and then they make an initial guess at the star's mass and some of those other properties, and then the system kind of iterates. Is that how it works?
Yeah. So I think they just got those properties from the data already. So use that as an initial guess, or error bounds to fit in this model. Then they can to get the composition and the age of the stars.
Okay, so that mass is already known. I was kind of thinking they guess at the mass, and then there's some iterative process, and then kind of the final mass is achieved. And what I was wondering is, if someone makes a really terrible guess, does that cost a lot more CPU hours to calculate? But it sounds like maybe that's not quite the way it works.
I think they can use very bad guess, but still it's because their iterations break in four jobs. So those 4 jobs like running parallelly. So if anyone cannot like what's that? Get to the point, then it will fail immediately. It won't take that long at all.
Oh, okay. That makes sense. Yeah, I agree with Sergio. This is a really interesting juxtaposition in ways that we don't often see, comparing observational data and computational simulation. So it's pretty interesting to a lot of us. Questions from other folks on the phone line? Okay, thank you very much. I did ask Haiying just to do a 20-minute talk today because we were expecting another presentation that unfortunately fell through very close to today's date. So we will conclude this month's symposium a little bit early with just one talk. And Haiying's contact information and her slides and also a recording of this event will all be up on the symposium website. And so we look forward to having everyone join us next month for our October symposium, hopefully with 2 speakers. So.
Good. Thank you.
Yeah, thank you very much for the preparation, Haiying. Thank you.
Thank you, Haiying. Bye-bye.
Thank you.
Bye-bye. You're welcome.
Thank you.
Bye.